Okay, great. I guess we can start now. Let me share my screen. Is my screen visible? Can anyone confirm? Please unmute and you can tell me. Yeah, because I will not be able to read your messages, so feel free to unmute and ask any doubt. Okay. So yeah, so in the yesterday's session we have discussed about ER diagram and some relational algebra. We have discussed that. We have revised the concept. Now you can see previous year gate question based on ER diagram. So this is basically gate CSC 24 question, right? So can anyone tell me the correct answer for this particular question? We'll first solve these two questions. It's previous year question from gate CSC paper based on what we have discussed yesterday, right? Then we can continue with the normalization topic here. Okay, today's topic is basically normalization part. So can anyone tell me the correct answer for this particular question in the context of owner weak entity set in the ER diagram? Which of the following statement is true? The weak entity set must have total participation in the identifying relationship. Is this true? Owner entity set must have total participation, or both weak and owner entity set must have total participation, or neither weak entity set or nor owner entity set must have total participation. Which of the options is correct here? This question is
Option
Sir, B.
option A must be true.
yes. Option A is correct here, right? So if you look at what we have discussed in the yesterday class here, right? This is basically this diagram we have discussed, right? So E2 is strong entity set and E3 is basically weak entity set, right? So here we have total participation of E3 in the relationship here, right? So E3 is basically weak entity set, right? So weak entity set must have a total participation in identifying relationship. Why? Because we know that weak entity set cannot exist without the strong entity, right? Because if you look at the nominee and the insurance holder example, right, unless we have an insurance holder we cannot have a nominee. So there must be total participation here. Total means what? It will start with 1 to n here, right? This is what we have discussed. So based on that you can see one question in gate 24 paper, simple question for 1 marks. So if you understand what we have discussed in yesterday's session, this type of question you can expect for 1 marks in gate exam. Okay. Now let's try to solve this question. Question number 39 from GATE 25 paper, CSC branch. This question was for 2 marks based on the TRC here. Okay. So you can see we have a two relation, teams and players. So TID and T name is given to us. PID, P name, TID is given to us. So which one is common? TID is common. Which one of the following tuple relation calculus query returns the name of a player who play for the team having T name as MI? Can anyone tell me which one is the correct here?
Sir, A.
Okay, so let's see. We want to project what name of the player. So P name is there. Now their P belongs to players. Okay, and there exists T. Okay, such that T belongs to teams. Okay, so here we have covered both the tables because we need to join the tables because we want to project what the player name here, right? And our required condition is on the T name. It means what we need to join both the tables. You can see here we have a P belong to players and T belong to teams. We have a joining criteria and the required condition here, right? So option A is correct here. What about option number B? Why it is not correct, or what's the difference here? What's the difference here? Looks same only. Okay, so
Sir,
here
here there is P belonging to teams. That is not right.
T belong to players here. Okay, so no, we can have anything, but here what we are projecting P dot P name, but players P name is in players table, so P must be players table. So here we have T, so simple, not correct. What about C?
There is no joining condition.
No joining condition. What about a D? D also, yeah, you can see here they have exchanged the P and T here, right? So simple question, right? So in the case of TRC and relational algebra, what we have discussed or DRC part. So first check for the required tables here, right? Required attribute or required tables is getting covered or not. Second, joining condition, right? Third one, where condition means our required condition, right? And fourth one is basically what we want to project, right? So projection here you can see. So if all these four things are covered properly, then the expression will be correct here. You can see projection is not correct, joining is missing here. Here also we have not projected and joining is missing here, right? So this is what we have discussed in the yesterday's class. So let's try to discuss about the normalization concept here. It's a very important topic, normalization. Every year, if you look at GATE CSC or GATE DA, at least one question will be there from this particular topic. Okay. So this covers multiple topic here. Functional dependency. Okay. Then we have decomposition part and all the properties and the key related to functional dependency concept, right? All these things. Then we have different normal forms, decomposition, and then we have dependency preserving also, right? Dependency preserving, all these are important concept, okay? And it's all links to normalization concept here. Okay, so we'll not go why this normalization is required, so we have discussed that in the lecture, you can just go through that. So we'll discuss about what is functional dependency. So when I say A determine B, what does this mean? Yes, anyone can tell me what is A determine B here?
A prime attribute determines non-prime attribute.
No. Prime and non-prime deals with the candidate key here, right? So when I say A determine B, so let's say for example, in the relation we have three columns A, B, C, right? So A determine B, FD means what? A uniquely determines B. It means if the value of A1, A2, A3, A1, we have like this four values, and A1 is corresponding value of B is basically B1, and B2, B3. Now see, if A1 determines B means what? If the value of A1 gives me B1 here for B here, then in the entire column A1 should give me B1 only. So here A1 should be B1 only. It's not like that A1 will be B2. Otherwise A1 will not uniquely determine B1. You can consider this as like this: roll number determine name, right? So roll number is unique here. So roll number uniquely determine the name here. It is not possible that two students have the same roll number, right? So the roll number is unique for every student. Name can be duplicate. Name can be duplicate here. B1, B1, B1. That is possible. But left hand side value uniquely determines right hand side value. Okay. This is basically concept of functional dependency. A uniquely determine B. So roll number is unique and name can be duplicate as well in the table here. So A1 can give me B1, A2 can also give me B1, A3 can also give me B1, but A1 must give me B1 here. Okay. So this is regarding the FD here. Okay. So we have different properties of functional dependency here. So you can see this question is basically GATE CSC previous year question. We'll discuss more about the functional dependency using this particular question here. Okay. So suppose the functional dependencies hold on the relation U. So U is given to us relation. Attributes are P, Q, R, S, T. We have 5 attribute and the FD is given to us. So P determine QR and RS determine T. So P determine QR and RS determine T. So here we have a relation U having column our attribute P, Q, R, S, T, right? So P determines QR means what? Here we have a combination here, QR, right? So if I say the value of P is basically P1 and value of Q is 1 and value of R is also 1 here, right? Then P2 can take Q1, but the combination here you can see Q1 R1 on the right hand side, that is fine. Okay, so Q1 again can take R1 here, P3 can take Q1 R2 like that. But if I have P1 again in the column, it must be Q1 R1 only. So left hand side value uniquely determine right hand side value. Okay, here this is about the P determine QR. Now there is one property. Okay, so we'll discuss that property later, but let me take the second FD here. RS determine T. Now on the left hand side we have a two attribute R and S here, right? So if I have R1, if I have S1, and let's say for example T1 here. So combination of R and S must be unique. So R1 S1 determining T1. R1 S2 can determine T1 or T2 because right hand side value can be duplicate here, right? R2 S2 can also determine T2 or T3, whatever the value of T will be. But again, if I have R1 S2, so R1 S2 determine T2, so R1 S2 must determine T2 only, like that. So here we have to check for a combination of R and S here, right? So R1 S1, R1 S2, these two are different combinations, right? But combination must be same here, like that together. I hope this thing is clear what we have discussed.
Yes,
Anyone,
sir.
any doubt? Okay. Now, if I have P determine QR, so there is one rule, union and decomposition rule. Union rule is what? If I have P determine Q and I have P determine R, so by union rule, I can say P determine QR. That is fine. Decomposition rule is reverse of this. If I have P determine QR, then I can write P determine Q and P determine R. This is fine. But this both the rules, union and decomposition rule, is applicable to only right hand side value, not the left hand side value. We cannot write R determine T or S determine T here. No, this is not a valid FD here. Okay, we cannot decompose the left hand side value here. Okay, we can only decompose or we can apply union to a right hand side value. Also, if R determine T and S determine T is given to us, we cannot say R is determine T here. No, that's it. That is not fine. This is not correct. Okay. Also, this is basically union decomposition. We have one augmentation here. Now, what is augmentation? If P determines Q, right? So I can add any attribute on the left hand side, a b c d z a z, anything, right? So a z p will determine q also, x p will also determine q also. If p determine q is there, I can augment any attribute on the left hand side. That will be a still valid fd here. Okay, that is basically augmentation here. I hope these three things are clear. Anyone, any doubt? No. Okay, great. So let's read the question carefully. Which of the following functional dependencies can be inferred from the above functional dependencies? Right. So we have a 2FD here, right? So what about A? Is A is true here?
No, sir.
Okay. So in order to solve such question, we should be knowing the concept of closure here. Okay. Closure of an attribute. Closure, right? So when I take the closure of any attribute, let's say for example ps here, right? Ps, right? So closure, we use plus symbol here like this, right? It's a set here, right? So ps will determine ps itself, that is fine. Now from p or from s or from ps together, which attribute I can get here? So from P, I can get Q and R. So I'm going to add QR in the closure. Now in the closure, I have P, I have S, I have Q, I have R. So from P or S, from Q or R, or combination of any two attribute or any three attribute, what I can get? We have RS also here, S and R determine T. So T also I can add here, right? If PS is giving me all this attribute in the closure, it means what? PS can determine all these three attribute Q, R, T as well. Okay, so you can see if PS is determining Q, R, T, then PS will give me T here. So option A is correct here. Okay, so closure of an attribute here. So if whenever you are taking closure of an attribute, so first write down the attribute which we are taking the closure, for example ps. Then from p or from s or from combination, which attribute we can determine using the fd here. So you can see I have p, so I have added qr also. Now from psqr, which attribute I can add? You can see here rs determining t. Okay, that is basically ps closure equals to this one, right? And now if you are taking the closure of any attribute, if you take the closure of attribute here, okay, attributes or set of attributes here, if that closure gives you r means what? All the attributes in the relation. Okay, so here we have pqrs. If the closure is giving us all the attributes, right? That is basically what? So that attribute or set of attribute will be my candidate key. Not candidate key, we can say simply key here. It can be a candidate key or super key. Okay. So if I take the closure of any key, that should give me all the attributes in the relation. That is basically a thing here. Okay. If you look at the GATE CSC previous year question, they ask for which of the following is basically key of the relation here. There are four options. So what you need to do, take the closure of left hand side in every option and see whether you are getting R or not. R means all the relations here, all the attributes here, all attributes I am saying in relation. Okay, this is what the closure of an attribute is. If you look at here, PS is giving me PQRST, all the attributes. It means PS is basically a key here. Okay, it is basically a key of this particular attribute. Now, can anyone tell me, is option B correct? Is option B can be inferred from the given FD?
No.
No, sir.
No. So simply you can take the closure of R. Do we have T in the closure? If I take the closure of R, from R can I determine anything? No, we cannot determine anything. Here we have RS, not individual R. So R closure will be R only. We don't have T. Not correct. What about P determine Q? P determine R? Is option C
Yeah.
correct?
Yes.
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 You can see directly here, P determine QR. So by decomposition rule also we can say, or even if you take the closure of P, we are going to get QR here. So R will be there. So option A and C is correct. What about option number D?
That is also correct.
Yeah. So if I take the closure of PS here, okay. So either you can apply all these rules, you can get that, or the best way, go for the closure. In the GATE exam, always go with the closure thing, because uh, finding out which rule to apply, then see. So best way is to find out the closure here. So if I find the closure of PS, what I'm going to get? So from PS, from P, I'm going to get QR here, right? So that's it. In the closure of PS, we have a Q, so we can get this as well. Okay, so A, C, D are the correct options here. Anyone, any doubt in this particular question? What we have discussed? Yeah, 9 participants. Okay. Okay, great. So this regarding the functional dependency. Okay. Now, what we have discussed about the key here, right? So if any relation is given to us, FD is given to us, we need to find out the key, right? So how to do that? Let's try to solve one question. So I hope the concept of FD is clear to everyone. Now we'll discuss about the key here. Do we have any question? Yes. This is also previous year question. We'll try to solve this. So we have a relation R having all the attribute with the following three FDs here, right? A, B determine C, B, C determine D, C determine E. We need to find out number of super keys in the relation R, right? So we have two things. When we say key here, that is basically candidate key, and then we have a super key, right? Now, what is candidate key here and what is super key here? So basically, candidate key is also super key, we can say, okay? But super key is not a candidate key, right? So candidate key is basically minimal super key. Candidate key is basically a what? Minimal super key, we can say. And how we can find out the super key? So let's say, for example, if A is the candidate key, now I can take the combination of candidate key with any other attribute, that will be my super key here. If A is the candidate key, then AB, AD, ACE, all these are basically my super key here. Okay, even candidate key is also super key. So if you understand this one, let's try to solve the question here. So here we need to find out number of super keys. Now what I just said, if we know the candidate key, we can find out number of super keys, because anyway, the combination of candidate key with remaining attribute will be my super key, right? So here if you observe how to find out the candidate key first, candidate key. Okay, so see, the conversion method is you need to check each and every attribute. Take the closure of A, see whether you are getting all the attributes in the relation R or not. Then take the closure of B, see whether you are getting all the attributes in the relation R or not, right? So that you have to do. But we don't have time for that, so we can apply one trick. First, find out the attribute which are not present on the right hand side of any functional dependency. So here I have C, here I have D, here I have E. So C, D, E. Which attributes are not present on the right hand side of any functional dependency? That is basically AB. So AB is not present on the right hand side of any functional dependency. So AB must be a part of candidate key. It can be a candidate key or it can be a part of candidate key. But first we have to check whether it's a key or not. How we can check that? Simply take the closure of AB here, right? If I take the closure of AB, so AB will give me AB, and from AB I am getting C here, right? Then I have ABC. From BC I will get D here, and I have C here. From C I am getting E here. That's it. So I'm getting all the attributes in the relation R. It means what? AB is basically my candidate key here. So AB is candidate key. That's it. Okay. Here we have only one candidate key here. Okay. So first always find out the attribute which are not present on the right hand side of any functional dependency. Okay. So then we have to take the closure of that attribute, see whether it's a key or not. And let's say for example, if I take the closure of AB and I am not getting E in that particular closure. Okay, let's say for example, it means AB is not the key. Then we have to check for the combination of AB with the remaining attribute. Remaining means what? Whatever the attribute which is not present in the closure with that attribute only. So here I have E is not present, so I can take the combination of AB with E. And then if I take the closure of ABE, that will give me all the attributes in the relation R. In that case, ABE will be my candidate key here. Okay. So first find out the attribute which are not present on the right hand side of any functional dependency. Then try to take the closure. If in the closure, if we have all the attributes, then it's a key. Otherwise, we have to take. Otherwise, we have to go for a combination of attribute with this particular candidate key. The attribute which are not present in the closure here. Okay, so this will be a thing. Okay, so try to practice more. Now here we got the candidate key. Now once we got the candidate key, we have two things: prime attribute and non-prime attribute. Okay, prime attribute, and second one is non-prime attribute. Now what is prime attribute? The attribute which are part of candidate's key. The attribute which are part of candidate key, that is basically my prime attributes. You can see A and B. So A and B will be my prime attribute. And what are non-prime attribute? Remaining are my non-prime attribute. That is basically C, D, E here. This is very, very important step. If you look at a normalization question, in almost every question, we need to find out the candidate key. We need to find out the prime attribute and non-prime attribute here. Okay. I hope how to find out candidate key is clear to everyone. Anyone, any doubt? Okay, fine. So now the question is number of super keys. Can anyone tell me how to find out number of super keys? We have a dedicated video on this number of super keys. Yes, anyone?
It is that 2 power, I think, difference between the total number of attributes and the number of attributes in the candidate. That is the total number of attributes minus the number of prime attributes.
Yes. So total number of super keys basically what? To the power n minus m. N is basically what? Total number of attributes in the relation. M is basically what? Total number of attributes in the key here, right? So this is basically what? For each key. For each key we are finding out the corresponding super keys here. Okay, if you look at, I just have one key here, AB. So in that case, number of super key will be what? To the power 5, and M is basically 2 attributes, that is basically 8 as an answer here, right? This is only for one key we have AB. Then number of attributes are 2. If I have just A, number of attributes will be 1. Then 5 minus 1 will be the answer, that is basically 16 here. But what if I have A and B individual candidate key? So A is also candidate key and B is also candidate key here. I have two candidate key. In that case, how to find out? So this is basically case 1. Case 1 is what? We just have one candidate key. That's it. It can be individual, it can be a group of attribute, that is fine. Case 2 is basically what? We have multiple candidate key. So for the exam purpose, they will only ask for up to two candidate key only, because for three candidate key it will be become a mathematical problem here. Okay, so case 2. Okay, so we have two candidates key here, A and B. Another case 3 is basically what, we also have two attributes but one attribute in common. So AB is there and BC is there, so these two are the candidate key here, right? So in all these cases answer will be different. So if any question, if I have two candidate key here, so first find out number of super keys using one candidate key. Let's say for example A, that is basically to the power 5 minus 1 for this relation, that is basically 16. Same for here as well, 5 minus 1, 16, right? But if you observe, if I take A as a at key, then ABC will be my super key, ABD will be my super key, ABDE will be my super key for A. In the case of B also, BCA will be my super key, BDA will be my super key, BDEA will be my super key. So all these are basically repetition here, you can see in both those things. So we need to subtract those combinations here, right? So how we can do that? So I hope you remember this formula. So number of A intersection B is equal to n of A plus n of B minus n of A union B here. So A and B is basically number of super keys using one candidate key, number of super keys using another candidate key, and here the union of both the candidate keys. So if I take the union of A and B, so AB will be there. It means what? I have two attributes. So in that case, so first using A, second using B, minus using both A and B, that will be 8 here, we know, right? So in total, we are going to have 32 minus 8 will be 24 as a number of super keys for this particular case, right? In the case 3 here, have AB and BC. In that case, using this and using this. So using AB will be what? 8 here, right? Using BC also will be 8. But what about the combination of AB and BC? So if I take AB union BC, that will be ABC here. Only 3 attribute, not 4, because B is repetitive. So that is A union B, right? So we have to take the union of both the keys. Now here I have 3 attributes. Now we need to apply this particular formula to the power 5 minus 3, that is basically a 2, that is basically 4 here. So in that case, answer will be a what? 12 here. I hope all the cases are clear for finding out the number of super keys. These three cases are only possible. Okay, that's it. Single one, double one without any common. Here, third one is basically two keys, but having one key as a common. Is this clear for the number of super keys? Anyone, any doubt? Okay, fine. Here we have.
So can you
Huh?
explain the third case once, the having one common key between them?
Yeah. So if I say we have two key A, B and B, C here, right? Right. So in that case, first find out number of super keys using A, B. That is basically to the power 5. So the total number of attribute minus this one, two attribute, that is basically what we have 8. Similarly, using this key, that is basically 8 also. But now if you look at here, number of super keys using one candidate key, number of super keys using another candidate key, but there will be some common combination as well. We have to remove those, minus number of super keys using A union B. A union B means what? Candidate key 1 union candidate key 2. So in that case, you can see A, B, C will be in the output, because B is repetitive. In union, we don't take the duplicates, right? So A, B, C will be there. If I have A, B, C, here I have C, B, E. In that case, A, B, C union C, B, E will be what? A, B, C, E, like that. Okay. So here, now I have three attributes. So using three attribute, how many super keys are possible? That is basically to the power 5 minus 3. That is basically a 4 here. So this is what we have done. 8 plus 8 minus 4 equals to 12.
Okay. Yes, sir. Got it.
Okay.
The same union logic which we applied for case 2. The
Yes.
only thing is here there are three, so that's the only
Yeah.
difference.
Here we have duplicate here B. So B will
Yeah,
be only once. Yeah,
yeah,
like that. Okay, great. If I have AB and let's say CD, then AB union CD will be ABCD only. That's it. So we have to consider this one for the number of super keys here. Okay, great. So this is regarding the total number of super keys and how to find out them. Now prime attribute, non-prime attribute is clear, right? So candidate key, super key is clear. So if you come across the question, whenever you need to check for a key here, so just take the closure of key. Okay. If you take the closure of any key, candidate key or super key, it should give me all the attributes in the relation R. That's it. Okay. So this is about the key here in general. So we have discussed about the FD here. Okay. Anyone, any question? So this is fine. Okay. Now let's discuss about a different decomposition here, right? So FD part, do we have any other concept? We'll see. So what is decomposition here? Lossless or lossy decomposition here? Lossless or lossy decomposition. Let's say for example I have a relation R, I have a big relation. Let's say for example 20, 30 rows are there, right? It's difficult to manage or manipulate the data in that table. So what we do, we will decompose that particular relation into multiple tables, right? We want to achieve certain normal forms here, right? So what is different normal forms, we'll see. Let's say for example I want to decompose this R into R1 and R2, like that. So while designing a database, we never decompose this R into R1, R2, R3, R4 directly. No. First we decompose this into R1, R2. We'll see whether requirement is satisfied or not. If not, then again we'll decompose this R2 to again R3, R4, like that. Okay. So that's how we decompose the tables, right? Now, if I have R, if I want to decompose this relation to R1 and R2 here, so there are a few conditions we need to satisfy for a lossless decomposition. We always want to achieve lossless decomposition here. Now, what is lossless decomposition here? Since I have decomposed this R into R1 and R2, it means what? If I join these two relation back R1 and R2, I should get the original relation R here, then only we can say it's a lossless decomposition here. If we are not getting the original relation back, then that will be a lossy decomposition here. Okay. So I hope lossless and lossy is clear. Now, how to check for a lossless decomposition? Three conditions are there. First one, R is equals to R1 union R2, means all the attribute must get covered. If I have 20 attributes in this particular R, so all 20 attributes must be part of R1 and R2 here, right? So together must be get covered like that. So R1 union R2. Second one is basically what? R1 intersection R2 is not equals to empty set here. The question can be asked based on these three things as well, 3 points as well. You can see previous year GATE CSE question. There is one question, right? 1 mark question for lossless decomposition here, right? 2014 or 2015 question was there. Third one is basically what? R1 intersection R2 should determine either R1 or determine R2 here. Okay. So first condition is clear. It means all the attributes should be get covered. What about second condition? What we can say about second condition? Yes, anyone?
There must be a common attribute between them.
Yeah, there must be some common attribute, right? So not empty set means what? There must be some common attribute so that we can perform the joining operation. If there is no common attribute, we cannot perform the join operation. And what about the third one? That particular common attribute must give me R1 or R2. It means what? That particular common attribute or set of attribute must be a key of R1 or R2 here. That is what the R1 intersection R2, we have R1 or R2, right? So you must have seen in the SQL schema, right? We make a foreign key. Foreign key references to a primary key of another table. So why we are making primary key of another table? Because there must be some common attribute and it should give me R1 or R2 here, because after joining we can get the original relation back here. Okay, so you can see this R1 and R2 here. I hope all these three conditions are clear to everyone. Any doubt, any question? Okay, fine. So this is regarding the lossless decomposition here we have. Now how to apply those particular condition? Let's see. So this is also one previous year question. So here we have a relation R. Here we have this PQRSTW. So number of attributes we have, and FD is given to us. Consider decomposition of relation R into a constituent relations according to the following decomposition scheme. So here we have two decomposition R D1 and D2. We have to check which one is lossy and which one is lossless. Okay, so this question was for 2 marks here. Okay, now see, if I say let's check for D1 here. So here I have 1, 2, 3, 4. So R is decomposed into R1, R2, R3, R4, right? So in the exam, we have to check whether it's a lossy or lossless decomposition. So how to check for this one? So first criteria. So in the previous case, what we have discussed, we just take two attribute for decomposition here, right? But this is how we decompose the table. If I want to check whether the decomposition is lossy or lossless, then you can see for this type of question, what we need to do. R must be equals to R1 union R2 union R3 till union Rn. Doesn't matter how many decomposition we have, R1, R2, R3, R4 or any other. So we have to take the union of all those things. If you take the union of all the decomposed relation, that should be equals to R. So if I take the union of all this one, let's see, we have P, Q, S, T, and P, T, X. So P and T already available. X will be added. Q and Y. So Q already there. Y will be added. Union Y, Z, W, and Z and W we are going to add here. Okay. So this is what I got. Is it the relation R here? P, Q, S, T, X, Y, Z, W. Yes, we got the relation, right? It means our first criteria is satisfied. If we didn't get all the attributes, it means it is a lossy decomposition directly. Okay, so is this clear how to check when we have multiple decomposed relation?
We
Any
have,
doubt?
sir, we have to
Okay.
take the union of the decomposition and then it should result into the original relation. That's it, right?
Yes, all the attribute must be there, correct. The
Sir, is it not like we have to preserve the functional dependency? Like PQ is determining X, right? So shouldn't the decomposition be like P comma Q comma X and then something like that?
no, we'll discuss about dependence preserving as well. Okay,
Okay.
yeah, in upcoming slides question. So first step is this one. Then once we have checked for this criteria, we have to check for another thing. Now remember what we have discussed. We take two sorry. We have to take two decomposed relation, any two relation, R1, R2, R3, R4. Okay. So any decomposed relation. In a such a way, there must be some common attribute. You can take R1, R2 because P is common. You can take R1, R3 because Q is common. Any two attributes, right? So let's go for R1, R2. So R1 intersection R2. What is common attribute here? P and T. Okay, so we have PT as a common attribute. Now, if I take the closure of PT, it should give me either R1 and R2 or R2, sorry, right? So remember those three conditions, right? So first take any two decomposed relation such that there must be some common attribute. And that common attribute must be a key of R1 or R2. So how to check whether PT is the key of R1 or R2? Simply take the closure of PT here and see whether we are getting R1 or R2. So if I take the closure of PT, what I'm going to get? So from PQ, I'm going to get X, but Q is not missing. So from P, I'm going to get YX, so I can add YX here, right? If you observe what we got, R2 here. P also present, T also present, X also present. It means what? This determine R2. It means what? I can join R1 and R2 here. So we are going to join this one. So say R12 equals to R1 union R2. Why? Because if I join, I will get how many attributes P, Q, S, T, X. This much number of attributes we are going to get. So this is basically R12. So we have checked for this two. Now let's go with R3 and R4. Do we have any common attribute? Yes. So let's say for example R3 intersection R4 here. You can also consider R12 intersection R3, R12 intersection R4. That is also fine, okay? But you can take any two decompose relation here. So I'm taking R3, R4 here. Now see what we are going to get. Y is common here. Now whether Y is a key of R3 or R4, is it a key of Y3 or R4? Can anyone tell me?
Yes.
Yes, you can see if I take the closure of y, I am going to get yzw. So that is basically R4. It means what? I can join these two relation. So say R3 4 equals to R3 union R4. That is basically what? Q, Y, Z, W. Now I left with R12 and R3 4, right? So I must be able to join these two relation. Now R12 intersection R3 4 is equals to what? So PQSTX QYZW. So I guess Q is only common here, right? Yes, Q is only common attribute here. Now from Q I should get R12 or R34. Now let's see what we are going to get from closure of Q. From Q I am going to get Y. From Y I am going to get ZW, right? And P I don't have. Okay. So you can see QYZW, that is basically my R34 only, right? So I'm getting R34. It means what? I can join this R12 with R34 such that I'm going to get R1234 which equals to R. So D1 is basically a lossless decomposition here. Anyone, any doubt what we have discussed? Okay. So try to solve more questions based on the lossless decomposition here. So this is basically for D1. Okay. Now can you check for D2? Yes, anyone can try for D2. We have R1, R2, R3, R4. First check for this condition. Is it satisfied? Do we have all the attributes?
Yes.
P, Q, S, T, X, Y, Z, W. So all attributes are getting covered. Now which attribute we have to consider? Any two attributes such that there is common attribute. So which attribute we can go? R1, R2, R1, R3, R1, R4. Any
R3,
combination?
R4.
Okay. So let's go with R3, R4 first, right? So R3 intersection R4 here. That is basically what we have Y. So if I take the closure of Y, am I getting R3 or R4? Yes, you can see. So YZW, that is basically R4. It means I can join R34. So R34 will be equals to what? R34 union R3 union R4. So QYZW here. Okay, we got R34. After that, what we need to do? Yes, anyone? R1, R2 is remaining. How to proceed? Yes.
Intersection with R1 because
Yes.
Q is common.
Okay, because Q is common, so we can take R1 intersection R34, right? So that is basically Q is common. So if I take the closure of Q, am I getting R1 or R34? QY will be there, and from Y I'm going to get ZW. So I'm going to get R34, right? So that is fine. I can join R1 with R34. So R134 basically what? R1 union R34. So that will be what? R1 is P Q S, then we have Y Z W here. We got R134. Now what is remaining? R2. So do we have any common attribute with R134 R2? We don't have T, we don't have X as well, right? So R134 intersection R2 is equals to what? Empty set, right? So this violates my criteria for lossless decomposition. So D2 is basically a lossy here. Okay. So D1 is lossless, but D2 is lossy decomposition. That is basically option number A is correct here. Okay. So this is how you need to check for a lossless decomposition here. Okay. So in the exam, definitely they will give for a 3-4 decomposition like this only. Anyone, any doubt in this case, what we have discussed in this question?
Sir, one doubt. Why are we taking R1 intersection R3 for? We can directly take R1 intersection R3, right?
R1 intersection R3 here.
Yeah.
Yeah, that also we can take. So Q will be there. So from Q I can get Y. So I can join R1 with R3. But at the last, I should be able to join all the four relations here, right? You can take any two decomposed relations such that is common attribute. Okay.
Okay.
But at the last, we should be able to join all the attributes like that. R1, 3, 4, like what we have done for here. R1, 2, 3 equals to R, like that. Okay. So this is regarding the lossy and lossless decomposition here. Okay. So this is about the decomposition form. Then we have a normal form here. So let's discuss about the normal forms.
Sir, I had a doubt.
Yes.
Sir, in the last question, uh, in the first condition, that is R is equal to R1 union R2 and all that.
Hmm.
So we check for whether all the elements are there in D1. So in case if it doesn't cover all the relation doesn't cover all the elements,
So
then it would be no decomposition like that.
yeah, it's a lossy decomposition, yeah, directly. So we don't need to check for any this further step. If this is not satisfied, then that's it. Okay.
But
Let's say for example,
it still would be decomposition, right? I mean, it
it's a
is still
lossy
decomposed into something.
it's a lossy decomposition.
Understood. Okay, okay, fine.
Yeah.
Got it.
So if I say X is not present here, so in that case, we see we are not going to get X. It means what? You have decomposed R into such a way one column is missing entirely, right? So we don't want that any column to be missing in the database. So that is what lossy decomposition here.
Also, sir, in D2, if we can, visually see like
Huh.
in the second one, T comma X,
Hmm.
so we can directly see that T is not common in any of R1, R2, R3, R4. So directly we can say it is lossy, right?
Yeah.
Without
So
calculating everything.
yes, yes. If you see both T and X is not present in any one of the relation here, then you can say like it's a lossy.
Got it, sir.
Yeah. So that will come via practice. So here we that this is what we check, right? Any common attributes is there or not. That's it. If we go for this one, T is common, no. X is common, no. If any attribute in the particular decomposed relation is not common, then that's a lossy decomposition, we can say. But we need to check for each and everything. Okay. Here we just have two attribute. What if this is also common? What if this is not satisfied? Right? So we need to go for all the possibilities here. Okay, great. So let's discuss about various normal form. So we have one NF, then we have two NF, then we have three NF, then we have BCNF, then we have four NF, right? So up to four NF they ask in the exam. We have five NF, six NF, but it's not important. In CSO also they have not asked any question based on that. So what about one NF? No, one NF means what? No multi-valued attribute. Can anyone tell me what is multi-valued attribute? Domain must be atomic.
Or something like an address. You should not have street number and plot number and
Yes,
phone code,
yes.
something like
So let's say, for example, here we have a phone number as a column, right? If and I have two phone numbers. If I am putting both the phone numbers in the same field, 888, one phone number, comma 918, like that. That is basically multi-value attribute here. If I have this kind of column in which I am putting two values separated by comma or any other separator, it will be difficult to update this particular entire column here, right? So we don't want that. So domain must be atomic here. So only one single field should be there in the particular column. Okay. So no multi-word attribute here. And how we represent this MVA in the ER diagram, by which symbol? multi-value attribute? Double ellipse is basically a multi-valued attribute here. Okay, so this symbol is used for to represent MVA here. Okay, that's it. So first one and a half is basically what? No MVA, domain must be atomic. In the question, you can see in many question in the normal form they will specify domain is atomic, right? Or even if they specify, you can assume that it is in one and a half unless mentioned in the question that any attribute is having this multi-valued condition. Okay, if multi-valued condition is missing, it means what? We can assume it is in one and a half, but most probably they will specify domain is atomic or there is no MVA. Okay, that's it. There's only one criteria for one and a half. What about two and a half? So first thing, it should be in one and a half first, right? So no MVA plus no partial dependency. No partial dependency. How to check for partial dependency? First, find out the candidate key. Second, find out prime attribute and non-prime attribute. Okay. So once we know how to find out candidate key, then prime attribute is basically a part of candidate key. Non-prime attribute is remaining attributes here. Once we find out that, then we can find out partial dependency here. What is partial dependency? Subset of candidate key. Subset of candidate key determining non-prime attribute. If this FD is present inside my functional dependency set, then it will be a partial dependency. This is not allowed in 2NF. Okay. Let's say for example, AB is basically my candidate key here. Okay, AB is my candidate key. And in the FD set, I have B determine D. So B subset of candidate key AB determine non-prime attribute, right? Just a second. 1 minute. Hello? Okay. So any subset of candidate key determining non-prime attribute is basically what? Partial dependency here. If AB is candidate key or A or B determining any non-prime attribute, that is basically a partial dependency here. Okay, remember this one. This is not allowed in 2NF. What about 3NF? It should be in 2NF first, it should be in 1NF first, and no transitive dependency. No transitive dependency. Now, what is transitive dependency? Non-prime attribute determining another non-prime attribute. Remember this, right? So once we find out prime attribute, non-prime attribute, check for NPA determining NPA. If this is there, it means it is not in 3NF. It is not allowed in 3NF. It's a transitive dependency here. Okay, it is not allowed, right? This is about 3NF. What about BCNF? Left hand side of every functional dependency must be a key. Okay, so if I have FD set and all the FD set in all the FDs, left hand side must be a key. Yes, any doubt? Anyone? Okay, but before that it should be in 3NF. Now what about criteria for 4NF? It should be in BCNF first, or something, sometimes it's called as 3.5NF also. Okay, 4NF is basically what? No multi-valued attribute. No multi-valued dependency, sorry, not attribute, dependency. Okay, we represent multi-valued dependency by A multi-determine B. So double arrow you can see here like that. That is basically multi-valued dependency, right? So this is not allowed in 4NF. So there are very few questions based on the 4NF in entire GATE CSE paper, right? But we'll discuss about MVD also, right? So this is not allowed in 4NF. Okay. So if I have this 8 multi-determine B, okay, that's it. So we can say it is not in 4NF. But condition is for 4NF, okay, not for 4NF, for MVD. For MVD to be exist, for MVD to be exist, there must be at least three attribute. So at least three attribute must be there. Okay, remember this one. At least three attribute must be there for the MVD to be exist. If only two attributes are there in the relation, if I have a relation just having two attributes A, B, no need to check for any normal form. It is already in 4NF. Already 4NF, BCNF, 3NF, 2NF, 1NF. It is in all normal form. Any relation having just two attribute, it is in 4NF always. Okay, so you can remember this. You can eliminate the options by using this particular property. I hope the conditions are clear. Any doubt? Yeah. Let me change.
So
Yeah.
the BCNF part, in the first whatever key is there, for example, X is determining some A, then the X must be always a super key. That is the condition.
Yes. Yes. So left hand side must be a super key. Okay. It's a
Yeah.
proper subset. Yeah.
So the 4NF, if we say something is in 4NF, then it is in BCNF as well, right?
Yes.
Okay.
Okay, so here it's a proper subset of candidate key, that is basically partial dependency. NPA determine NPA transitive dependency. For BCNF, left hand side of every FD must be a key. For 4NF, no MVD. Okay, so just remember this particular condition. That's it. You can solve any question based on this. But the given thing is you should be able to find out CK and PA and NPA here. This is very important. Okay, so let's try to solve one question here. This question is based on what FD concept we'll discuss. This question is also we'll discuss. Let's try to discuss this question, then I will come back to these two questions. So again, previous year GATE CSE question here. So we have two relation R1, R2 to FDs are given to us. We have to check for both the relation here, right? So first, what about R1? But the R1 is in 3NF, not in 3NF. We have to check same for R2 as well. Okay, it's a CSE 24 or 25 paper, I guess. So let's check for the R1 here. In R1, we have A, B, C, D, E. Can anyone tell me what's the candidate key here for R1 given the FD? Tell me what is the candidate key for R1? Similarly for R2.
AD will be for R1.
AD, we'll see. So first find out the attribute which are not part of right hand side of any functional dependency. So E is present, B is present, C is present, A and D is not present. So AD must be a part of candidate key. We are not saying AD will be a candidate key. AD must be a part of candidate key. So if I take the closure of AD, what I am going to get? So from AD will be there. From D, I can get E. From AE, I can get B. And from EB, I can get C. So all attributes are there. So AD is basically my candidate key. So I got the candidate key for R1, right? What are prime attributes? A and D. What are non-prime attributes? Remaining attribute B, C, and E are my non-prime attribute. That's it. Now tell me, it is in 3NF or not in 3NF?
Not in 3NF, because A determining D and A determining B means A determining B. So that's a transitive dependency, right?
Oh, sorry, can you repeat?
Sir, A is determining D, and then again A is determining
No,
B.
no, no,
So,
no. This is for R2. We're checking for R1. This
oh,
is
sir.
FD for R1.
Okay, okay, right. Sorry, sir.
Here for R1, tell me. It is in 3NF or not? AD is basically my candidate key here. Condition for 3NF, it should be in 2NF first, and then it should be there should be no transitive dependency, right?
So it's not 2NF, right, sir?
Why
D
it
goes
is not
to
in 2NF? Yeah, you can look at this FD here. D determine E, right? So proper subset of candidate key determining E here, right? So partial dependency, right? So it is basically not in 2NF. Okay, so R1 is in 1NF only. R1 is in 1NF. That's it. So it is not in 2NF, not in 3NF. Okay. So R1 is not in 3NF, that is correct. Okay, we are saying R1 is not in 3NF, it is in 1NF only. So option C is correct. What about R2? Now tell me directly about R2. What's the key here for R2? A, B, C, D. What's the candidate key for R2? Here we have FD.
C has to be the.
So DBA, C is not present. So we have to check whether C is candidate key or not. So let's check for C. So from C, what I can get? A here. All right, let me remove this. And yeah. So from C, I can get A. From A, I can get D. From A, I can get B here. So C is basically a key here. Now, is it in 3NF or not in 3NF? Can anyone check?
Not in 3NF because we have non-prime determining another non-prime.
Yes. So prime attribute is C, non-prime attribute is A, B, and D. You can see NPA determining NPA. It's a transit dependency. It is not in 3NF. So C and D are the correct answer here. Okay. So you can see this question was asked for 2 marks, right? So this type of question you can expect in the exam. So this question was in set 1, this question was in set 2. Same, I guess, but here we just have lossless decomposition part as well. Okay. So this is basically, I guess, a set 1 25 paper, set 2 25 paper for CSC. Now let's try to solve this question. Here we have a schema, team, name, city, owner with FD is given to us. Relation team is decomposed into T1, T2, right? So first check whether team is in BCNF or not. Let's check for option number A. So this type of questions are very good because here we need to check for each and every case here, right? Yeah. So if you want, I can I will add exercise for this type of question, MSQ question. I've added this type of question in the test series part, subject wise test part. Yeah, a test series we have a subject wise test in the test series, right? In that you can see one question like that. So first tell me about the option number A. Is team is in BCNF or not in BCNF? Again, first find out the candidate key for team. Team is this particular relation here. What's the key for relation? Team. FD is given to us. City and owner. City owner. So only name is there on the name is not present on the right hand side. So name must be a part of key. If I take the closure of name, his name is the key. Yes, from name I'm going to get city as well as owner. So all the attributes of name is basically a key. Now tell me, it is in BCNF or not now? Hello? BCNF or not? We have just two FD here. Name determine city, name determine owner.
So they are in BCNF.
Okay. They are in BCNF. Okay, fine. So please unmute and tell me. Otherwise, I need to check the messages. Okay. So it is in BCNF. You can see left hand side is the key. Left hand side is the key. That is fine, right? So once left hand side is the key, so that's it. It is in BCNF. So A is not correct. What about B? Relation T1 and T2 are in BCNF. Yes, we have
Yes.
discussed that any relation having just two attribute already in BCNF, right? Option B is correct. But let's say, for example, in any decomposed relation, we have three attribute: name, city, and let's say, for example, name, city, uh, country. Okay, let's say, for example, country. In that case, how to find out this decomposed relation is in which normal form? For that particular purpose, you need to find out F1 such that all the FDs applicable to T1 you have to write down in the F1. Then you have to find out the candidate key for T1. Okay. So here we just have two attributes. That's how we can directly say it is in BCNF. But if we have three attribute, so first find out all the functional dependencies applicable to F1, right? And then find out the candidate key and then see whether it is in which normal form. So that thing you have to do. Here we can directly say it is in BCNF, so option B is correct. Is the lossless decomposition? This one T1, T2, is this correct? Simple one to check.
Correct.
Yes, so R1, so T1 union T2 giving me all thing. Then name is common attribute, and from name I'm going to get any one of the relation, both the relations. So C is correct. Relation team is not in 3NF. No, not in 3NF. No, not correct. Okay, it is in BCNF. Can we say it is not in 3? Oh no, it is in BCNF, so already in 3NF. Yeah, correct. So only B and C is correct here. Okay. So I hope you understand what we have discussed here, right? If any relation, decomposed relation, if we have more than two attribute, then we have to find out all the averages applicable to F1. Okay. And then based on that, we have to find out candidate key. FD means what? Based on the parent FDs, we have to write down in F1 here. Okay. This is about the normal form, and we have two questions from the previous year. So yeah, can anyone tell me which of the following statement about relation R is in first normal form? Which option is correct? Get 2024 question. CSE paper. We just discussed this one and F. R can have multiple attribute.
A only, sir.
No, R can have multi
It can
attribute
cannot
key.
have. Yeah.
R cannot have a foreign key.
So C is the answer. Composite attribute.
Cannot have a composite attribute. Hmm. Composite attribute. Composite attribute. It can have composite attribute. Uh, R cannot have foreign key. It can have foreign key as well. R cannot have composite attribute. R cannot have more than one candidate key. Mhm. Let me check the answer here. Question number 22 of GATE CNC paper. So till then you try to solve this question. I'm checking which is the correct answer here, because R can have multi-attribute key. Multi-attribute key. Multi-valued attribute. Multi-attribute key. Different thing. Then A is the only correct option, because R can have foreign key. Cannot have composite attribute. Composite attribute is there. Cannot have more than candidate key. It can have. So this is not anyway correct.
So,
Multi-attribute, they
well, but in 1NF, all the attributes must be atomic, right? Then,
yes. So
so he asked which of the following is or are not true, right? So C must be an option since R cannot have a composite attribute.
composite attribute, right? So composite attribute, does it mean multiple attribute? Name
So
is
composite attribute would have its own three tables, right? Like for name is a composite attribute that will have first name, last name, middle name. So three different tables will be
that is
there, right?
composite table, huh? That is what
So
composite attribute is.
so it can have them,
It can have composite attribute. This is what I'm saying. Yeah. Address is composite attribute. Address can have three component like that, right? This is the symbol for composite attribute in ER diagram.
Yeah.
This is correct. So just a minute, I am checking the answer key. Let me go for a next slide. You can try to solve this question first.
Sir, it should be first option, no? Then multi attribute key,
Yeah, it should be first option only. But
because key can be composite, right?
yeah, they are saying, oh, it's a key or attribute. It's a key, right? So R can have multi-attribute key. Yeah, it can have a key. It cannot have multi-attribute, a multi-valued attribute, but it can have a key. Yeah, key is there. So option A is correct. Correct. Let me check. Let me verify once. Till then, you can solve question number 44. I will just verify that question number 22. Just a second. Let's see. Paper.
Sir, in that in notes also you have given this in the example.
Uh, this example.
Yeah, so you gave one table in that there was a multi-value attribute, and you said then we have to convert it into a table which has like first it had two tuples, then it will have three tuples. So then in the first one, the primary key was roll number, but since now there will be two rows of roll numbers, now the primary key will be changed to a composite key that will be roll number plus student, like that.
Yeah. So composite key can have. So just want to verify option A is correct or not. Just a second. It cannot have multi-valued attribute. Multi-attribute key is possible. Question number 22. Which of the following? That's a question. Yeah, I guess set one. Question number 22. A and C is the correct option here in the official answer key for that particular question number 22. A can have multi-attribute key, cannot have composite attribute. Okay. One normal form deals with the M multi-valued attribute only. Multi-valued attribute. Which of the following is true? Okay. R cannot have composite attribute.
Maybe
I
what
guess
they are
they are
saying.
saying composite this one, entire this one, right?
Correct.
Yeah, yeah.
So
Not the
something like
components here.
address. I think I
Yes,
mentioned
yes.
address, right?
Yes,
Yeah.
yes, correct, correct. If I just put here full name, right? So they are saying they cannot have full name, like first name, middle name, last name together, right? That is what composite attribute. I can have three different columns like this, but this is thing this composite one. Yeah, it cannot have composite attribute because it will be difficult to update then. If I have just full name column and I have all the my first name, middle name, last name in the same field, then I cannot update the second last name or middle name here, right? So if I want to do any correction, so option C is correct here. Yeah, option A and C is correct. It's a key. We can have a key. We cannot have multi-or attribute. Okay. Sorry for the confusion. Yeah. I hope this thing is clear why A and C is correct. Here we're talking about this composite attribute, not the component of this attribute here. Okay. What about question number 44? Here, what we are trying to see functionally dependency in the context of database. Okay. If this is given to us, can we say X determines ZW?
No, sir.
No. We already discussed in the first slide itself. What about this one?
Yes, this is
Yes. Decomposition rule, correct. What about this one? Implies X W Z. If X Y determines Z, can we say W determine Y? So together can we say X W determines Z? So best way to take the closure of X W based on these two. That's it. Okay. So X W will give me X W, and from W I will get Y. So X W, and from X Y I'm going to get Z. So X W I'm going to get Y Z. So X W Z. This is implies. What about D? X give me
correct.
y give me z. So we can say x determines z. The transitive dependency we say, and even you can take the closure of x here, see whether you are getting z or not. So in this type of question, just take the closure of left hand side and see whether you are getting right hand side value or not. Okay. So option B, C, D is correct here. Okay. So this is regarding the FD here. So you can see this type of question also you can expect. This simple question for 2 marks, right? So we need to understand. Okay, great. So we have discussed about the normal form. So just remember this particular slide. So all the conditions, and then what is dependency preserving here, right? So let me quickly discuss that. Yeah. So let's take this example itself. Okay, let me create one example here. Let's say, for example, here I have R, A, B, C, D, E, and the functional dependencies basically A determine B determine C, and D determine E, like that. And let's say, for example, D determine EB. Okay, let's say, for example, we have this FD here, right? Now, what is dependency preserving, right? Let's say, for example, I'm decomposing R into A, B, C. R2 will be my DE, I'm going to add A here. Okay. Let's say, for example, we have R1 and R2. Now I need to check whether dependency is preserved or not after decomposing this into this one. So first find out applicable functional dependencies to R1. So here you can see A determine B will be there, right? B determine C I can add here, right? So first from the parent FD only try to add FD in the F1, F2 or whatever decomposition we have. So we have added these two in F1, F2. Can we add this in F2 or F1, this FD? Yes, anyone? D determine EB. So we have D, we have E. Do we have B in that R2? No, it means we cannot add that. But if you look at, I can write down this DE and DB here like this. It means what? I can add this FD in F2. So D determine E here, right? Which one is remaining? From the original one, D determine B here. Now I cannot add DB in R2 as well as R1 because there is no D in R1, there is no B in R2. So for such case only we have to check for dependency preserving. If after decomposition all the FDs are getting preserved automatically in R1 and R2, then no need to check. We have to check for only those FD which is not getting preserved directly. Now, how to check for this one? It doesn't mean that it is not preserved. We have to check for that. Okay. So first, find out all the FDs applicable to F1, F2. Is this the applicable FDs, or do we have more FDs also? Can anyone tell me? I guess I have recorded one session, video on dependency preserving as well. So see here, A determine B, B determine C. But can I add A determine C also here in F1 as, right? I can do that. What about F2? Determine E. Can I add E determine something or A determine something? No, right? So that's it. Here we have, that's it. Now this is remaining. What we have to do? Take F plus, that is F1 union F2. Okay, so all these 5 FD we have to consider 4 FD, right? That will be A determine B, B determine C, A determines C, and D determine E. Okay. So first, what happened? Just a minute. Yeah. So first find out all the F's applicable to F1, F2, then F plus such that F1 union F2. So we got this one, right? And then find out the this FD here. Take the left hand side of that particular FD D here and see whether we are getting B in the closure or not using this F plus. Take the closure of D based on F plus here. Are we getting B? No. It means what? D determine B is not preserved in the relation here, in the decomposition here. That is what a dependency preserving is. I hope you understand this particular concept. Anyone, any doubt here? Hello? Okay?
सर वो F1 फंक्शनल डिपेंडेंसी में ए सी कहाँ से लाए आप? वो आप डिटरमाइन कर दिए क्या? A to B, B to C, then A to C.
A to C, right? See,
हाँ,
A to B or B to C directly I can write down from parent functional dependency, right?
yes.
What is F1? All the applicable functional dependencies based on R1 here. So if you look at transitive dependency, A determine B, B determine C, so A determine C, right?
Mhm.
So all the FDs you have to write down here. Okay.
And then we just have to add that all. Okay,
Yes.
add all those things, then come. Get
Then
the
check
thing.
for this one. Yeah. If I have here B determine A, let's say for example B determine A also, right? In that case, I will add B determine A, not B determine A. Sorry, E determine A. If I have E determine A, so I can add E determine A in F2, right? I can add E determine A here. Now you can see D closure, D will give me EE, DE, and from E I can get A, that is DEA, right? And from A I can get B, that is B here. So D will give me B here, like that, right? So this is a dependency preserving now. Okay. So you have to check, you have to follow this particular process. You cannot say directly that D determine B or not. Okay. Okay. So that's it from my side. Any doubt what we have discussed today? Okay, just a second. Okay, great. So this is about the normalization and dependency preserving. Okay, so try to solve more question based on this, like all the previous year GATE CSC and DA question, all the test series question. If you have any doubt from the normalization topic, you can ask in the next session. Okay, so next session will be on Sunday. Okay, not tomorrow. Sunday we'll meet.
Sir, I had a
Huh?
doubt.
Yes.
Sir, is like candidate key similar to primary key?
No, see, while designing a database, first we find out the candidate key. And let's say, for example, we have two, three candidate key. Now, out of this three candidate key, then we can decide which will be my primary key. Okay, that is basically a primary key deals with the creation of a database here in SQL. If I have a candidate key, and out of any candidate key, I can set as a primary key. Now, what is super key? Super key is basically a combination of a candidate key with any other attribute, right?
Okay, so so these two things are different. Like candidate key and primary key is different.
No, candidate. So primary key is basically candidate key only. Okay. So while designing a database, first we find out candidate key. Okay. If I got two candidate key, let's say for example A, B, and C, D. Now database designer will decide which key we have to make it as a primary key in the table. We can make AB also. We can make CD also. While creation of table.
Okay, understood, understood.
Yeah.
Right.
So this ER diagram normalization deals with a database design. Primary key deals with while creation of a database in the SQL. Okay.
Sir, another question. What is like composite attribute and multi-valued attribute, are they same or different?
No, no. Composite attribute is different. Okay. So just a second. Let me share it again. See, composite means what? Let's say for example you have address here, right? So address will have the flat number, it will have the pin code, right? It will have some taluka or district, like that. So address is a composite key having this particular component, right? This composite key, we represent a composite key in ER diagram by this particular symbol, like that. Multiple attribute is basically what? Double ellipse. So MVA will have phone number, or phone number and one phone number in the same particular field, two phone numbers in the same particular field, like that. This is basically a multi-valued attribute. So multiple values are present inside the attribute. That is multi-valued attribute. Multiple values are in the same attribute here. Composite is not a multiple values here. We are storing this address in this particular format. If you look at my first name, last name, and middle name and last name here, this is basically my composite name, right? But individually I can store in the database, like that. I can store this in the particular column also, but it will be difficult to update if I want to update a last name, middle name, like that. Okay. So if I have multiple values in the particular column, that is multi-valued attribute here. Okay. This is not a multiple value here. Here we have different components of a particular attribute, we can say. In address also, flat number, pin code is different components, right? But here phone numbers are the component here. We are keeping two values in the same particular column. Same field, we can say. I hope this is clear.
Yes, sir. Yeah.
Okay.
सर एक डाउट था
हाँ.
सर इस लेक्चर में नहीं रिगार्डिंग नॉट दिस सर
Okay.
थियोरी क्लासेस में आप जो पढ़ाए थे वो कोर्स में उसमें मुझे 3NF एंड BCNF में थोड़ा डाउट था कि क्वेश्चन सॉल्व हो जाते हैं कोई इशू नहीं आता लेकिन ये थोड़ा फंडामेंटल डाउट ये है कि जैसे कि BCNF में क्या होता है कि लेफ्ट हैंड साइड में बोल रहे थे कि मतलब कोई सा भी बस की होना चाहिए बट मतलब थ्योरी में ये होता है कि BCNF का लेफ्ट हैंड साइड सुपर की होना चाहिए, और सुपर की नहीं है तो राइट हैंड साइड में प्राइमरी एट्रीब्यूट होना चाहिए। ठीक है ना
हाँ।
सर?
हम्म।
एंड 3NF में लेफ्ट हैंड साइड में की होना चाहिए,
नो
एंड
थ्री एनएफ,
उसमें भी आप,
थ्री एनएफ में एनपी
हाँ,
डिटरमाइन एनपी ये नहीं
हाँ,
होना चाहिए, बाकी सब चलेगा।
हाँ, ये नहीं होना चाहिए, बस कोई सा भी की होना चाहिए, सुपर की हो गया या कैंडिडेट की हो गया, कोई सा भी की हो तो वो 3NF में आएगा।
हम्म।
अगर वो BCNF में हो तो सुपर की ही होना चाहिए लेफ्ट हैंड साइड में, या कोई सा भी की हो तो चलेगा।
नो एवरी की इज
वो
बेसिकली
एक्चुअली,
सुपर की, एवरी की सुपर की ही है।
हाँ,
हाँ, तो
हाँ,
बस की होना चाहिए, सुपर की होना चाहिए लेफ्ट हैंड साइड। जरूर नहीं कैंडिडेट की ही चाहिए, सुपर की भी चलेगा। ओके।
ओके। तो सपोज कोई केस हो एंड उसमें मैं पहले मिल गया कि लेफ्ट हैंड साइड का की, मतलब लेफ्ट हैंड साइड में की ही है, तो
हम्म।
फर्स्ट आई विल कंक्लूड दैट इट विल बी लाइक ए 3NF। देन उसके बाद मैं शो करूंगा कि ठीक है, वो नॉन प्राइम से प्राइम नहीं होना चाहिए, अगर ये तो वो भी CNF में नहीं है, तो ऐसे डिडक्शन करना पड़ेगा, ऐसे है ना सर?
नो ऐसे फर्स्ट चेक फॉर वन एनएफ, टू एनएफ, थ्री एनएफ, बी सी एनएफ। ओके। सो पहले ये सब चेक करना पड़ेगा, वन एफ में है, उसके बाद टू एनएफ चेक करो, उसके बाद थ्री एनएफ चेक करो, उसके बाद बी सी एनएफ चेक करो। रिवर्स नहीं जा सकते हम।
नहीं सर, एक क्वेश्चन एक्चुअली ये था जिसमें कि
हाँ।
ऑप्शंस में सिर्फ 3NF एंड BCNF में मतलब इन दोनों में डिस्कशन चल रहा था,
ओके।
एंड आई वाज कॉन्फिडेंट कि मैं आंसर सही कर दूंगा, लेकिन गलत हो गया इसी वजह से कि आप ये बोले थे कि लेफ्ट हैंड साइड में की है तो ठीक है, मैं 3NF श्योर था तो मार दिया। एंड BCNF में भी की होना चाहिए, सुपर की होना चाहिए, लेकिन उसमें भी की था, तो मैं BCNF में सिर्फ सुपर की ढूंढूं या की ढूंढूं?
नो सुपर की एक ही है, सो एवरी की इज बेसिकली सुपर की ओनली।
ओके।
अगर मैं बोलता हूँ कि बी इज अ कैंडिडेट की है, सो बी डिटरमाइन ए, लेफ्ट हैंड साइड इज अ की, बी बी सी डिटरमाइन डी, बी सी भी तो सुपर की हो गया ना अगर बी की है तो। सो ये भी चलेगा बी सी एन एफ में, इट शुड बी अ की।
Sir, but there's a scenario that it's in 3NF but not in BCNF. That
हाँ, वो वाला क्वेश्चन शायद वो भी किया।
इट्स इन थ्री एन एफ बट नॉट इन बी सी एन एफ।
हाँ सर।
सो मतलब वहां पे ट्रांजिटिव नहीं है। ओके, सो वो कौन सा कंडीशन रहेगा, लेफ्ट हैंड साइड इज नॉट द की हियर, राइट। सो वो भी रह सकता है क्योंकि ये भी प्राइम एट्रीब्यूट डिटरमाइनिंग अनदर प्राइम एट्रीब्यूट, राइट। ये वाला अगर केस बनता है तो इन दैट केस इट विल बी थ्री एन एफ बट नॉट इन बी सी एन एफ, बिकॉज प्राइम एट्रीब्यूट इज नॉट द की हियर, राइट। Let's say for example I am saying BC is basically my candidate key here, right. And if you look at BCD determining another prime attribute, okay, let's say for example D is also my candidate key here, so BCD determining E here, so AB prime attribute hai, AB prime attribute hai, this is fine, okay. But on NPA determining NPA जो है वो 3NF में नहीं चलेगा। Also you have to check whether this is not a subset of candidate key, otherwise वो 2NF में नहीं होगा। नहीं, 2NF में भी हो सकता है वो, because my right hand side is basically a prime attribute, right? If you look at all the three conditions what we have checked, NPA भी NPA, अगर राइट हैंड साइड में तुम्हारा प्राइम एट्रीब्यूट आ रहा है तो 2NF में होगा, 3NF में भी होगा, बट इट विल नॉट बी इन BCNF अनलेस लेफ्ट हैंड साइड इज द की। समझ रहे हो, अगर राइट साइड में प्राइम एट्रीब्यूट आ रहा है तुम्हारा, इट विल बी इन 2NF, इट विल बी इन 3NF, बट नॉट नेसेसरी इट विल बी इन BCNF, बिकॉज उसके लिए लेफ्ट हैंड साइड तुम्हारा जो की होना चाहिए। हेलो।
सर लेकिन थ्योरी में एग्जैक्टली यही वाला पॉइंट है सर, कि थ्योरी में ऐसे लिखा है कि लेफ्ट हैंड साइड मस्ट बी अ सुपर की, otherwise if left hand side is not super key then right hand side must be a primary attribute, a prime attribute.
दैट इज बेसिकली फॉर 3NF, राइट।
हाँ,
वो 3NF के लिए होगा। BCNF के लिए मोस्ट स्ट्रिक्ट कंडीशन है देन 3NF, लेफ्ट हैंड साइड मस्ट बी अ की, दैट्स इट।
अच्छा, ठीक है।
Sir, so in BCNF, we don't even bother about what is there in right hand side, irrespective of it is prime or it is non-prime,
Yes,
right?
left hand side must be a key. Key determining non-prime or prime doesn't matter, but it should be a key. That's it. Okay. So this is regarding the BCNF here. If right hand side is a prime attribute, so you don't need to check for 2NF, 3NF. Okay. But for BCNF, we have to check because for that left hand side must be a key. That will be a case of 3NF, but not in BCNF.
Okay, sir, understand.
Yeah. Okay. Chalo. So that's it. We'll see in the
Sir, I
next
had
session.
a doubt. Sorry.
Okay.
Not exactly doubt, but sir, when I was doing the AI course, right, in the last, we have proposition and predicate logic, right?
Huh.
So in predicate logic, we have that for all and there exist.
There exists symbol. Yes.
Yes. So when I was doing questions, right, I was able to do the questions like 80% of such. But sometimes when the combination of for all and there exists, when it is combined, right, I'm still not able to understand the English translation or the grammar properly. I tried practicing the
Uh,
this, whatever you gave, but still.
Okay. So for that, just check equivalence rule there, right? So if I take a negation of that one, so what will be in the result case, right? So for that, you require practice for predicates. Proposition is simple one. For predicate, we need more questions to solve.
Sir, any specific thing that I can, apart from the thing you have given, anything else I can do? Only that portion I'm having issues.
Yeah. So you can solve previous year question of discrete mathematics, GATE CSC paper. So in discrete mathematics, we have this predicate and propositional logic. Try to solve all the questions. Anyway, I have covered all this question in my video itself, course itself. So try to
सर
solve.
ये रिवीजन सेशंस कब तक खत्म हो जाएगी, मतलब आपका स्केड्यूल कैसे है?
शेड्यूल तो भी मतलब संडे को होगा, संडे टू फ्राइडे कंटिन्यू होगा। सैटरडे संडे में नहीं रहता हूँ, थोड़ा काम रहता है, राइट? सो या इन द वीक डेज 6 to 7 p.m. daily we are going to meet.
Okay.
Yeah. So I will just message you in the discussion forum. Okay. So you can check out that. Anyway, you are going to get a reminder before 10 minutes.
Sir, it will be great if we have some sort of a schedule, right? Like, if first we'll do
Uh-huh.
AI, okay. So we can be more prepared then.
Yes, yes, that's what I'm planning. So I will create a schedule. So anyway, we have completed almost 50% of DBMS. So we'll complete DBMS, then we can go for PDSA or AI. Okay, whichever you prefer. So I will share the schedule and then we can follow that. Okay. Okay.
ठीक है.
Great.
Thank you, sir. Thank you
So
very much.
chalo. Thank you. Bye bye.
Thank you, sir.
You can find a recording also after the session.